Quantum computers have the potential to be the most important, the most dangerous, and the most unpredictable invention of our lifetime. They can even become all three of those things all at the same time. We hear this term come up every now and again. It sounds very futuristic and speculative, but quantum computers are very real. They exist right now, and they are on the verge of becoming a big part of our daily lives. One thing that Professor Pym does have right is that the smaller things get, the stranger the laws of physics that govern them will become. This is important to keep in mind as we go along. You've probably seen a quantum computer before. It looks pretty weird, more like some kind of a cross between a golden chandelier and a giant squid than anything we traditionally associate with a computer. But that's largely because our current viewpoint is a little too narrow. This thing is also a computer. The first computer, actually, as in the first ever. It was found at the bottom of the Mediterranean Sea and dates back to ancient Greece. It is known as the antitheta mechanism. It was used to predict the movements of the sun, the moon, and the earth. It could have forecasted a solar eclipse decades in advance, the same as we can today. And this computer also looks pretty weird. Although these shiny golden mechanisms you're seeing are just artistic recreations, the real artifact is actually a bunch of fragments encrusted with thousands of years' worth of ocean gunk. Calculating machines have taken many forms over the centuries that they've been used by humankind. So in many ways, the quantum computer is just a next phase of evolution, but in many other ways, it's not that at all. Modern computers, as we know them, are defined by bits. A bit is the smallest unit of data that a computer can process and store. Bits are the building blocks of every piece of digital information you have ever experienced. A bit is always existing in one of two states, kind of like a switch. This is why we say that computers speak a binary language. The state of each bit is typically represented by either a 1 or a 0, but it can also be represented by on or off, up or down, left or right, as long as each bit is holding one of two potential values. This is binary computing. The physical manifestation of a bit is called a transistor. This is like an electronic switch, and again, it can exist in one of two potential states, on and off. So the more physical transistors you have, the more bits of information you can process at one time, which is an oversimplification, but it gets the point across. So we've been constantly trying to make these transistors smaller and smaller over time so that we can fit more transistors into increasingly smaller devices. This old desktop calculator from the 1960s used 250 transistors. A current model iPhone has 19 billion transistors in its main processor chip alone. To accomplish this, we have reduced the size of the transistor down to a width of just 3 nanometers. This is too small for the mind to truly comprehend. It's only slightly wider than a strand of human DNA, which is 2.5 nanometers. It's possible that transistors could be reduced to the size of 1 nanometer by the end of this decade. There is a physical limitation on how small they can be, but regardless of how small you make a transistor, it is still limited by the binary nature of the bit. It can only ever be in one of two states, and this is where quantum computers come into play. A quantum computer uses its own unit of data measurement, which is the qubit. But qubits can also represent both 1 and 0 at the same time. They are non-binary, and this essentially gives qubits the potential to hold vastly more information than traditional bits. And the physical manifestation of a qubit is achieved by manipulating the spin state of subatomic particles, either protons or electrons, causing them to spin up and down or left and right, creating two distinct states, your 1 and 0. Except quantum mechanics allows these subatomic particles to exist in multiple states simultaneously, so they can potentially be spinning in all directions all at once. Remember, the smaller things get the stranger the laws that govern them. Here's what that looks like. If you put two bits together, We know that each bit will represent either A1 or A0. So, regardless of the combination, you have 2 bits of information. But when you put 2 qubits together, you end up with the equivalent of 4 bits of information. This is because there are now 4 possible combinations of 1 and 0, because each qubit has the potential to be both values at the same time. So instead of just being 1 and 0, the pair could also be 0 and 1, or 1 and 1, or 0 and 0 all at the same time. If this is starting to sound familiar, then that's probably because you're already a quantum physicist, or you've heard about a thought experiment called Schrödinger's cat. The basic explanation of Schrödinger's idea is that you could take a cat and put it in a box, then put something else in the box that could potentially kill the cat, like a cup of poison. Then you seal the box again. Thought experiment. No one put a cat in a box with poison, at least not that we know of. Now, as long as there is no way for us on the outside to know what's happened inside the box, then we have no evidence to suggest that the cat is dead or alive. Maybe it drank the poison. Maybe it did it. My cat eats plastic, but refuses to eat chicken. They're unpredictable creatures. And as long as we have no observable method to predict the fate of the cat, then it may be considered simultaneously to be both dead and alive at the same time. This is referred to in quantum physics as a superposition, and it is a state in which our qubits are able to reside. There are 2 potential outcomes occurring simultaneously. Now the trick here is that the moment you open the box and check on the well-being of the cat, that superposition collapses back into a binary. The cat will either be dead or alive. And the same applies to qubits. They eventually have to pick a side and resolve as either A1 or A0. But that time spent in a superposition allows the quantum computer to explore a vast network of potential combinations before arriving at a final answer. This superposition is where the quantum computer gets its power. When you start adding up all of the potential values from the superpositions of multiple qubits working together, then you start to get some pretty staggering numbers. Remember when we said that 2 qubits were able to store 4 possible values, making them equivalent to 4 standard bits, while combining just 20 qubits together will produce more than 1 million potential values. The largest quantum computer that exists today that we know of was built by IBM and has over 1,000 qubits of processing power. In 1 decade from now, IBM expects that will increase to 100,000 qubits. Now, what does that mean for you and me? The first thing that we should establish is that quantum computers are not just a better version of our existing computers. They are less of an evolution and more like an alternative mode of transportation. Quantum computers can take us to places that we have never been before in the same way that your boat can take you places that your car can't drive. But a boat is not an improvement on a car or a substitute. So quantum computing will not be replacing 99% of the jobs that are currently done by existing supercomputers, and you definitely won't be adding one to your existing lineup of personal tech. The most simple reason for this is that in order for a quantum chip full of qubits to actually function, it needs to be held at a temperature as close to absolute zero as physically possible. This is as cold can be. It's colder than the vacuum of space. So, in order to even operate a quantum computer, you first need to obtain the world's most powerful freezer. Oh, and even with the necessary cooling system, existing quantum computers can only operate for around 1 second at a time before the qubits lose their superposition state. The second problem is a bit more difficult to wrap your head around, but in simple terms, quantum computers are actually able. Thank you for watching Hot Topics. Please help the channel by hitting that like and subscribe button. And don't forget to leave a comment below if you want to see more exciting videos like this.